Hello, everyone. Howdy. Wait a little bit longer for people to join up, and then I will get started. Oh, man. Hello, doggos. Looks like no one is going to join. No one else is going to join, so I will just get started. All right, so we are finished talking about electric fields, calculating electric fields by integration. Okay, so now we're going to move on to another concept in electric fields, and we're going to talk about that for the next 2 weeks, I think. So, and we're going to kind of build up the difficulty. So, let's go ahead and get started. So the first concept that I want to talk about today is something called the area vector, which is denoted by capital A. All right. And so the area vector, it points. So what you want to have here is you want to imagine some surface. So maybe this is a rectangle. So it has a length L and a width W. Okay. So the area vector points perpendicular to the surface. So this surface's area vector is going to point perpendicular to it. So perpendicular would be in that direction. So that's a right angle. Maybe I'll draw a circle as well. So here's like a disc, and the disc has a radius r. And so the area vector would point perpendicular to that. And then the size of the area vector is equal to the area of the surface. Okay, so this is a rectangle, and rectangles have an area of W times L, length times width. So my area vector is going to be W times L times its direction vector, which is in the J direction. Okay, this one's area vector, well, the size of the area of a disk is pi r squared, and then it's pointed in the I hat direction. So that would be the area vector for that disk. One thing that you want to notice is that there are really kind of two area vectors for a surface because there are two directions that are perpendicular. So for example, for this disk, it's equally perpendicular to have an area vector that points in that direction. Or for this surface, it's equally valid to have an area vector that points in that direction. So, the area vector has kind of two directions. You got to think about that. All right. So that is the area vector. That's the first concept for today. The next thing I want to talk about is I want to go ahead and review the dot product. Okay. And so the picture you want to have in your head when you talk about the dot product is you want to have two vectors, maybe v and w, and those two vectors have an angle between them. That angle is theta. And the dot product is denoted by v dot w, and it is equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Okay. Remember, one of the conventions is if you just draw the name of the vector without the arrow, that's the same thing as the magnitude. So I could also write it as just VW cosine theta. Now, because those don't have the arrows over the top, that's shorthand for magnitude. Okay? So, V with an arrow over the top is not the same thing as V with no arrow over the top. There are three cases of the dot product that are going to be of the most importance to us in this lesson. And one example is when both V and W point in the exact same direction. The other case is when V and W point in opposite directions. And the third case that is of particular importance is when V and W point at right angles to each other. Okay, so if the two vectors point in the same direction, then the angle between them is 0. Okay. If the two vectors point in opposite directions, then the angle between them is 180 degrees. If the two vectors point at right angles to each other, then the angle is 90 degrees. So what does this mean? Well, for all three of these vectors, V and W are the same. The magnitudes are the same, but it's the angle that's changing. So the cosine of 0 is 1. So in this case, V dot W is just going to be the product of the two magnitudes. Okay? In this case, the cosine of 180 is negative 1. So in this case, V dot W is going to be minus the magnitude of V times the magnitude of W. Because of so this minus sign is from the cosine of 180. And then if they're at right angles, the the dot product is going to be 0 because the cosine of 90 is 0. So these are the most common three cases of the dot product. Okay. So now what we will do is we will define the main topic for today, which is called the electric flux, also known as the flux of the electric field. So what you need two things. You need a surface, okay? So in the, like for example, this surface or that surface, and you need an electric field. That is defined on that surface, okay? And so the flux, fluxes are typically denoted by a capital Greek letter phi, and because it's the flux of the electric field, it is phi sub E for electric field, and it is equal to the magnitude of the electric field on the surface dot product with the area vector. Okay, so here's the picture you want to have in your mind. Here's the surface. All right. The electric field is defined on that surface. Okay. So there's the electric field. And then the area vector is pointed perpendicular to that surface, so that there's a certain angle between that electric field and the area vector. Okay. So it's fairly easy to figure out that the units of electric flux okay, the units of electric flux are going to be electric field times area. So electric field is measured in newtons per coulomb, and then area is measured in square meters. So it's Newton meters squared per coulomb are the units of electric flux. Okay, so some common cases for electric flux. So in this case, the flux is going to be EA cosine of theta. Okay. Please, please, please keep in mind that it is the area between the normal, or it is the angle between the normal to the area and the electric field. A lot of times people use this angle instead, which is a, I don't know, complementary or supplementary, whatever one is 90 minus the other angle. So you got to be careful to use the right angle, the correct angle, okay? In the case where you have an electric field that is pointed perpendicular to the surface, like this, okay? In this case, the angle is going to be 0, right? Because the electric field is perpendicular to the surface, and the area vector is also perpendicular to the surface. So you're going to get that the flux is just E times A. All right? If you have a situation where the surface is like this, okay, and the electric field is going parallel to the surface, like so, all right. In that case, you have, because remember the area vector is going this way and the electric field is going that way, so the angle is 90 degrees. And in this case, your flux is going to be 0. So in that case, this electric field gives zero flux through the surface. That electric field gives zero flux. Okay, I told my joke. I can continue on with my lesson. Sometimes, no, there's not an easier way to write phi. I mean, if you want to write a lowercase phi is just like that. So you can write it as a lowercase if you want to. That's, less lines. Or you can make up your own symbol. You should make up your own symbol for electric flux. Maybe your symbol is going to be... Okay? Make up your own alphabet. Sometimes... Okay? Sometimes a surface is made up of multiple subsurfaces. Okay, so we're going to make this a specific example here. So an example of that, let's suppose we have a all right, something that looks like this. So we're actually going to do the calculation here. So this is basically two faces of a shoebox, if you will. Two faces of a shoebox. So this is, let's say, 4 meters by 9 meters, and this is 4 meters by 4 meters. Okay. And then we have an electric field that is constant, both in magnitude and in direction. And so this electric field points in such a way so it points in the same direction okay, in such a way that it makes an angle of 30 degrees right here. Okay, so that angle is 30 degrees, and also this angle is 30 degrees. And the electric field has a strength of, let's say, 50 newtons per coulomb. Okay. So what do you do if you have multiple surfaces like this? Well, if you have a multiple surfaces, subsurfaces that make up the entire complete surface, then what you do is you simply sum up the fluxes through each surface. However many surfaces there are. Okay, so if there were 3, you would add up 3. Okay, and so when it is written in this way, because it's a sum, remember the integral sign is simply an elongated S for sum. So what they do when you have a complicated surface is you write it as the integral of E dot dA. So you're adding up, remember this is a sum, the electric field dotted with an area vector. Okay, so this is the more common way of writing electric flux. Okay, is writing it like that. And you might put a little subscript S to indicate that it is a flux integral over a particular surface. So this would be the surface S. And one thing I want to point out is that any vector field can have a flux integral. So later on in this class, we will talk about the flux of the magnetic field. Magnetic field is denoted by B, so this would be the flux of the magnetic field. In fluid dynamics, you oftentimes have the flux of the velocity of the fluid. That's related to how much fluid is flowing through a surface. So if you have a pipe and you do a flux integral across the cross section of the pipe, that'll tell you how much fluid is flowing through the pipe. So these appear all the time. Okay. All right. So let's do this calculation. So if we think about the flux through this particular surface, I'm going to have the top face, so the electric field on the top, dot the area vector of the top, plus the electric field on the side face, dot the area of the side face, because there are two faces on this surface. The electric field is the same here and on both of them. So it's going to be 50 is the electric field plus 50 is the electric field. The area of the top face is 4 by 9, so 36. The area of this face is 4 by 4, so 16. And then we have cosine of theta. So theta is the angle between the normal to the surface and the electric field. So notice how I gave you the angle. This angle is 30 degrees. But the normal angle of the surface would then have to be 60 degrees. So do not fall for that, particularly if you are taking the AP Physics C exam. I've seen lots of questions where they try to trick you by giving you the wrong angle. And really you're supposed to use the other angle because it's the direction of the area vector is perpendicular to the surface. So this would be 60 degrees. And then this, the normal to this face is going to point to the right. So that's the direction of the area vector. So here the angle actually is 30 degrees. Okay. So then we just work this out. So it just equals whatever Newton meters squared per coulomb. Unfortunately, Canvas will not allow you to submit whatever as an answer. So now I want to talk about closed surfaces. So sometimes a surface is so-called closed. Okay? A closed surface means that it's enclosing a volume of space. So that the only way to go from inside the surface to outside is if you pass through the surface itself. Okay? So these are not closed surfaces. This is not a closed surface because if you wanted to go from one side to the other side, you could just go around. Okay? These are also not closed surfaces because if you want to go from one side to the other side, you would just go around. But there are closed surfaces, okay? An example might be a cube. Okay. A cube has an inside and an outside. All right. Another example is a sphere. A sphere has an inside and an outside. Another example is a cylinder. Has an inside and an outside. So these are all closed surfaces. And you can calculate the flux of an electric field through a closed surface. When you are calculating the flux through a closed surface, you modify the symbol a little bit. Okay, and to indicate that it's a closed surface, you put a little circle here on the integral sign, because circles have no boundary, right? They're closed. So that's what you do if it's a closed surface. And I have to say, when I took AP Physics C in high school as a senior, and I first saw this when I saw this for the first time, I really thought it was cool just in the way it looked. I felt like I was really starting to understand something that most people probably wouldn't understand, and I hope you guys feel the same way. Like, if you just wrote this down and showed it to some random person and said, what does this mean? They're not going to be able to understand it or tell you what it means. So I started to get excited when I saw that for the first time. So maybe you do too. So let's do some examples here. So what if we have a cube, okay? And let's say that the dimensions of the cube, so we're going to turn each of these into examples, okay? The dimension of the cube, so the side length of it is, let's say, 3 meters. So it's a 3 by 3 by 3 cube. And on the bottom half of the cube, the electric field has 1 strength. Okay. And that strength is going to be 5 newtons per coulomb. And on the top, the electric field has a different strength. It's stronger. How do we know it's stronger? It's because I'm drawing more field lines for the top. Okay. And so it's defined everywhere. Okay, so it's and this electric field, let's say, is 15 newtons per coulomb. All right. So this electric field that's on the bottom part of the cube, it exists everywhere. Okay, so it exists over here as well. And this one exists everywhere as well. So how many faces does a cube have? A cube has 6 faces. So we're going to have 6 E dot dAs when we calculate the flux. Okay. So it's going to be the sum, I equals 1 to 6 of EI dot AI. But here's the thing. For the four faces that are kind of around the middle here, the electric field points up and down, but the area vector points side to side. Okay, so for those 4, the angle is 90 degrees, and so the flux is 0. So really the only ones that matter are the bottom one and the top one. Okay, so the four faces around the middle of the cube are this kind of a scenario, so they have no flux. So really all that's going to matter is the top one. So the electric field in the top dot the area of the top plus the electric field on the bottom dot the area of the bottom. Okay. Now when we have a closed surface, the area vectors point out by convention. So remember how I said back at the beginning of the lesson, I said that you have two area vectors. One goes one direction perpendicular, the other one goes the other direction. And there's no real difference between the two if you have an open surface. But if you have a closed surface, then you define like an inside versus an outside. And so now we can uniquely say what the area vector is. And the convention is that the area vector points out towards the outside. Okay? So on the top face, the electric field points up, and the area vector also points up. So on the top, we have an angle of 0 degrees. On the bottom face, the area vector points down, and the electric field points up. And so there we have an angle of 180 degrees, which gives that factor of -1. Okay? So what we get is looks like my transmission, my upload rate is fluctuating a lot. So what we get is for the top, it's just E top times A top. Remember, these are magnitudes. But for the bottom, you have that minus sign because of the 180 degrees, E bottom times area bottom. Both of these areas are the same because it's a cube, and every face of a cube has the same area. So for the top one, it's going to be 15 times 3 squared. And then for the bottom, it's going to be 5 times 3 squared. So that is going to give us 90 Newton meter squared per Coulomb squared for that example. Now, what about a sphere? Can be thought of as a single curved face. Okay, so a sphere has an area vector that points perpendicular and out. So the area vector points perpendicular and out. So it actually changes directions depending on where you are on the surface. Okay. What if we had an electric field, okay, that also points perpendicular to the surface and out? So this electric field is always pointed outward like that, so that it always has 90-degree angles with the surface. Okay, so there's another electric field vector. It has a 90-degree angle. Okay. Let's suppose that the size of that electric field is maybe again 15 newtons per coulomb. And let's say that the radius of this sphere is let's say 2 meters. All right. So we want to think of the sphere as a single curved face. Okay. And furthermore, because the electric field points out and the area vector also points out, we're going to have an angle of 0 degrees because the electric field always points out and the area vector always points out as well. So they're always going to be pointing in the same direction. Now, depending on where you are on the sphere, those two directions are going to change, but they always change together. So, you know, if you're over here, the area vector points out, the electric field points out as well. So the angle is 0. If you're over here, the area vector points out, but the electric field also points out. So wherever you are, the angle between the two is 0. So we're going to get that the flux through that surface is just going to be it's going to be 1 E dot A, because we're thinking of it as a single curved surface. And then the angle is 0, so it's just going to be magnitude of E times magnitude of A. So that is going to be simply 15 times the surface area of the sphere, which is 4 pi r squared. So 4 pi times 2 squared. All right. So that is 16 times 15. So what's that? 240? 240 pi or something? Newton meter squared per coulomb. All right. Lastly, let's do the cylinder. And let's say that this cylinder has 3 different electric fields. So we want to think about a cylinder. Think of a cylinder as 3 faces. All right. It has a middle face, middle curved face, which would be this part, you know, around the middle, okay, plus 2 end caps. All right. Cylinders have a certain radius, so we'll say for this particular example, the radius of the cylinder is 1 meter. And they also have a certain length. The length of this cylinder, let's say, is 4 meters. Now, each of these 3 faces is going to have a different electric field, okay? So on the left end cap, the size of the electric field is 10 newtons per coulomb. And this angle right here that it makes with the normal is 60 degrees. Okay? On the right end cap, the electric field points straight up and down. Okay? And the size of that electric field is 300 newtons per coulomb. Along the middle region, the electric field points perpendicular to that middle region. So the electric field is kind of doing like this sort of a thing, where it's always at a right angle to the surface. Okay. So this is all right angles here. Like that. And on this middle region, the electric field has a strength of 5 newtons per coulomb. And so what we want to know is what is the electric flux through this cylinder. Okay? And so it's going to be 3 parts because there are 3 faces. So there's going to be E dot A for the left end cap plus E dot A for the middle. All right, plus E dot A for the right end cap. Now here's the thing. For the right end cap, the area vector is going to point that way. So that's the direction of the area vector, and the electric field points up and down. So that means that the angle is 90 degrees, which means there is no flux. So this one, no flux. For the left side, the electric field points inward. So whenever you have an inward pointing, whereas the area vector points outward, you are going to have negative flux. So negative flux is when the electric field points into the surface. Positive flux is when it points out of the surface. So the left face is going to have a negative flux. The size of the electric field is 10. The size of the area is pi r squared. So pi times 1 squared, because the radius is 1. All right. And then the angle is 60 degrees. For the, and then this one was 0. For the middle region, the size of the electric field is 5. And then we want the area of this middle region. So you can think about the middle part of a cylinder as a circle that is stretched down the length of the cylinder. So that surface area is going to be 2 pi r times the length of the cylinder. So we have the circumference of a circle stretched along the body of the cylinder. So 2 pi r times the length times the cosine of the angle, and it's always 90 degrees. So this angle is 90 degrees, which gives 1. All right, so if I work this out, we get 5 times 2 times pi times 4 minus 10 times and we get about 110 plus 110 Newton meters squared or per coulomb. Okay? So there is a law, okay, in physics, and it is called Gauss's law. Gauss was a mathematician slash did a lot of things. Gauss's law. Ooh, if we want to write it in the German way, we could write that. Because Gauss was German. One of the most brilliant mathematicians of all time. And so what Gauss's law says, let's suppose you have a surface. Okay, so here's your surface. Oh, I'm sorry. Yeah, you're exactly right. This should have been 0 degrees. My bad. Really good catch. Thank you. Because remember, the area vector points normal. So this is cosine of 0 degrees is 1. So I multiplied this term by 1. Thank you very much for catching that. So this is some weird surface. All right. Made it kind of look like a potato. So we got this weird potato-like surface. Okay. And that surface has some charges in it. So maybe this is Q1. Maybe this is Q2. All right. Maybe this is Q3. Maybe this is Q4. So notice how we have, three charges that are actually inside the surface and one charge that is outside. So then what we do is, let's assume these are all positive, and we go ahead and make electric field lines. So we say, that's what the electric field's going to look like. So just drawing some electric fields. Okay. Okay, so we draw our electric field lines. And what we can see is that these electric field lines are going to pass through the surface. All right, so these electric field lines are all puncturing the surface. Okay, and so what we could do is we could calculate the flux of the electric field due to these charges. All right, and it turns out that it is equal to the charge enclosed by that surface divided by a constant of nature, which is called epsilon naught. So this is called Gauss's law. All right. So it relates the flux of the electric field through a closed surface to the charge enclosed by that surface. So in this particular case, okay, the charge enclosed in this particular case would be Q1 plus Q2 plus Q4. Because Q3 is not inside the surface. Epsilon naught is a constant of nature. It is called the permittivity of free space. Permittivity of free space. And its value is 8.9 times 10 to the minus 12. And it has weird units, farads per meter. Okay. So what we're going to do, so this is going to be a gradual buildup over the next 2 weeks. All right. So what I expect you to know how to do today, at least on a basic level, is how to calculate electric flux through a surface. Okay. And then what we're going to do next time is we're going to talk about the intuitive meaning of Gauss's law, because this is actually a really intuitive law once I have a little bit more time to explain it. And then we're going to show that it is possible to use Gauss's law to actually solve for the electric field. Okay. And then next week, we will apply Gauss's law to some fairly complicated scenarios and show that it's really, you can calculate the electric field quite easily using Gauss's law in some fairly complex situations. So it's kind of like, Gauss's law is kind of like a shortcut that allows you to calculate the electric field more easily than integration in some cases. Okay? So